Standard smartphones now connect directly to satellites in low Earth orbit. Artificial intelligence manages crop yields across thousands of hectares of farmland. Global enterprises process millions of data events every second. In 2026, information and communication technology operates at a planetary scale. Passing university-level exams on these systems requires a structural framework rather than rote memorization. We will use this 8-point ICT exam dashboard to break every technology down by its definition, importance, uses, advantages, disadvantages, examples, exam points, and summary. This matrix extracts the specific, testable metrics evaluators look for. We are focusing heavily on these last two boxes to ensure you are ready for the actual exam questions. Mastering these 8 metrics for 4 specific 2026 technologies provides the baseline you need to navigate the modern digital landscape. Let's start with data infrastructure. The data lakehouse is a hybrid architecture. It combines the rigid, governed structure of a data warehouse with the flexible, open nature of a data lake, often called a data swamp when it lacks organization. The lakehouse merges these two patterns into a single platform. This setup removes the need for duplicate data pipelines. Business intelligence teams and machine learning engineers pull from the same governed source. However, the high setup complexity creates a significant organizational learning curve. In the current market, platforms like Snowflake and Databricks provide the infrastructure required to run these lakehouse models for global enterprises. For your exam, focus on 2 defining traits: decoupled storage and compute, and the use of open table formats. These are the technical requirements evaluators expect you to identify. Smart systems rely on a biological-style relationship between the Internet of Things and artificial intelligence. IoT sensors function as the data-collecting senses, while AI operates as the central brain making decisions based on that input. We see this loop in precision agriculture. Soil sensors stream nutrient data to a cloud AI, which directs automated drones to apply water or fertilizer to specific coordinates in the field. Today, modern telemedicine uses this exact same feedback loop for remote diagnostics. While these systems offer continuous, personalized care, they require heavy infrastructure investment and can struggle with isolated data silos. The value of these systems comes from automated, real-time efficiency gains in food and health sectors. These results define the technology's impact, far exceeding the simple utility of the physical sensors. Next-gen telecom now includes direct-to-cell technology. While standard mobile data requires a nearby cell tower, D2C allows an unmodified smartphone to send signals straight to a satellite in low Earth orbit. Think about the physics of that connection. If you are sending a signal hundreds of miles into space to a fast-moving object, what is the primary advantage, and what is the biggest physical limitation? The advantage is total global coverage, effectively eliminating dead zones. The limitation is strictly limited bandwidth and the requirement for a clear line of sight to the sky. The signal cannot easily penetrate thick roofs or dense urban cover. The core exam takeaway is that D2C functions as a complement to terrestrial networks rather than a replacement. It provides critical messaging in remote areas, but is not designed for high-bandwidth home streaming. Digital systems rely on massive physical infrastructure. To sustain lakehouses and AI models, we require networked server racks demanding vast space and electricity. This is the sustainability paradox. Digital technology helps reduce global emissions through optimization, yet the infrastructure itself is a massive and growing consumer of global energy. Hardware obsolescence adds to this cost. Proprietary equipment and frequent digital upgrades generate millions of tons of electronic waste every year. Regulators address this through policy interventions and interoperability standards. The shift toward universal charging cables is a specific example of using regulation to reduce redundant manufacturing and e-waste. When answering questions on green computing, use the terms energy proportionality and hardware lifecycle extension. These are the high-value concepts required for a complete technical evaluation. This is your final cheat sheet. We have synthesized all 4 technologies: data lakehouses, smart systems, D2C satellites, and green computing into the 8-point dashboard. Capture this matrix for your records. You now have the definitions, real-world examples, and analytical trade-offs needed to succeed in your 2026 ICT evaluations.